Okay, so what's the situation like? How are you doing, people right there? Just let us know that you're there, maybe by just maybe shouting out or whatever, just clapping your hands. This is my man. Okay, thank you. Well, above everything, I just want to say that it's appreciated that you're just staying late until the very end, which just shows some respect towards all of the presenters for today, which is really appreciated from all of us. Me just saying it on behalf of all of the organizers and all the technicians and everyone who's involved in just keeping this, like a whole morning, afternoon ongoing for all of us. So it's called Code Dive. It's 2025 edition. It's the 12th edition, and we also saying that to the audience who is gathered all around the world by means of the computers and all the stuff which is programmed actually, and it's all about code again. So let me just leave it aside. I'm just a presenter. Okay, so first of all, I want to say that we have the last tidbit regarding Wrocław. And this time we will be talking about the persona who is so much connected with our place. So this is... Wrocław is just a UNESCO city of literature, by the way, so it has a deep literary tradition and is home to Nobel Prize winner Olga Tokarczuk. Maybe you know her from some of her books. They are pretty popular across the globe, so it's one of Poland's most celebrated modern authors. If you still haven't grasped anything from her, didn't catch any of the books in the library or in the bookstore, then feel free to do it because they are really interesting. But we'll be coming back to coding, and we have a guest from France. So our next guest is a French C++ expert working on, somehow it's in the brackets, historical VGO games. He has a love/hate relationship with build systems, but has moved his primary focus towards performance and multi-threading. In the past, he spoke at CCPCon, meeting C++ and ACCEU, and used to run the Paris C++ user group. Currently, Mathieu, because this is his name, lives in Sweden. This is Olga Tokarczuk, but ladies and gentlemen, on my left-hand side, on the other hand, we have Mathieu Ropert. So please welcome him very, very warmly, or even hotly. Just feel free.
Thank you. Is this on? Yes, amazing. Well, thank you everybody for coming. This is a huge room. This is a bit scary. This is the last talk of the day. There was a lot of code. There was a lot of very heavy topics. So today, to finish, I would try to offer you more like a kind of a story of a journey. My journey and also a historical journey because, as mentioned before, I'm kind of a history nerd. So I want to take you on a little trip through history and tech. So we're going to have to go back. We're going to go back to Bucharest. Our story starts in 1939, somewhere in September. It's a late evening, and a group of people are hurrying themselves toward the gates of the British embassy. They knock at the door, and they introduce themselves as mathematicians. They say they're Polish, and they said they have cracked the Enigma machine, and they're running away from the Germans, and they would like safe passage to London. Sadly for them, the personnel of the embassy of Bucharest has never heard any of those words before, and the best he can offer them is to come back in a couple days. They get a bit worried. They know that there is a bunch of informants for the Germans in the Romanian police, and they are obviously afraid to be caught. But they are undeterred, and so they press on and go to the French embassy, where they basically deliver the same story, but they're able to name one French officer that they before met in Paris. Again, the ambassador in France has no idea what this whole Enigma thing is about. But he has a phone. So he calls Paris and says, hey, I have those guys at the gate. I could do it in French, but for the understanding sake, I will keep it in English. I have those people at the gate. They claim to know this guy, a French military officer, and they say they have cracked Enigma. And luckily for them, they immediately get confirmation, yes, let them in. We'll send them to Paris as far as we can. Those people are from the Polish Cipher Bureau, and they're actually mathematicians, and they actually have cracked Enigma. And they will be granted safe passage to Paris, in which they will later continue their work. if you're anything like me, and you have heard like history from, I don't know, France, England, hopefully in Poland you probably have heard this story before, but if you're anything like me, you would be like, wait a minute, Mathieu, I thought Alan Turing cracked Enigma. Isn't that the whole thing? Isn't that the whole reason we are here, right? You know, like Bletchley Park, the whole Enigma team, they made a movie about it. You know, he cracked this whole machine and invented the first computer to do so. Like, is this a fan fiction you're telling us late in the evening? And maybe for you it is, but I assure you it is actually entirely true. So we're going to have a little discussion about this whole story. And the reason why I'm telling you this story is that a couple years back, in the summer of 2022, following a kind of a random discussion / dare, I went to ask myself, look, what about all those encryptions that we had back in the days, you know, like in very early days of computing, in the very early days of the modern era? Like, how good could they be today, right? Like, my thought was, look, sure, like Enigma sounds a bit complicated, but like I have a big computer now. Surely I can crack this in a few seconds, or can I? So during this talk, we're going to try to figure out exactly like what is the cryptography that is involved. After all, I think CodeDive told me, Mathieu, do you have a talk about C++ and safety? I was like, yes, kind of. So we're going to talk about historical safety, I guess, and we're going to use some C++. We're going to talk about breaking ciphers. There's going to be more history, because me. And there is some C++, I promise. There's not a ton, because I only have 45 minutes, but there is some C++. And basically the whole point of this talk is who would win, right? Like two nerds that are actually understanding math, unlike me, or like my 10th generation i7 and its 16 cores. An interesting match, I think. Not that I think I can compare to those two, but, you know, who would win? Interesting question. So first, let's talk about the Enigma machine, because I'm sure you all heard the name before, but I think a refresher on how it works would be interesting. Why does it exist? Well, you know, as we all know, all warfare is based on deception. I used to make strategy games, so just if you don't know anything about warfare, usually if you have bigger numbers, you win. That tends to upset players, but that's just the truth of most of the time. And so if you can't win with bigger numbers globally, you try to win with bigger numbers locally. You attack them when they're weak. Once we invented radio, that changed a lot of things. That allowed us to do very complex maneuvers and change the history of warfare forever. Unless the other guy can listen to what you're saying and knows exactly where you're arriving, because then you, again, lose your advantage. And so here comes Enigma. It's older than World War II, actually. It was invented on the last days of World War I, because originally it was not made to be used by the army. It was made for German companies who were trying to share trade secrets over telegraphs, and were really worried that someone was listening and would run faster than them to the patent office. So the idea was like, hey, if you are discussing like secret technology that you're working on with your different branch offices, you can do that secretly so that nobody can do corporate espionage. And what is fascinating about it is that there's no electronics in there. No, obviously the computer was not invented yet. Like, there is electricity, but there is no electronics. It's really a bunch of routers, a few wires, a lamp, and a battery. And it's portable, which is why it interested a lot the German army, because it's self-powered and portable, which means you can put it in a submarine, you can even put it in a tank or in a car, which means your commander can be in the field and almost live be transmitting like secret messages in Morse that the enemy cannot read. And you can decode them in a couple minutes with a trained operator. How does that work? So the base idea is a simple substitution cipher that you encode in a router. So basically you have like 26 pins on the right, which correspond to the 26 letters of the commonly used alphabet. And you have 26 pins on the right. And obviously they're not mapped, they're mapped one-to-one, but not directly. The idea is that you have some scrambling in the wires. So for example, the A will go to the E, etc., etc., etc. It's basically one implementation of a physical, like wielded substitution cipher. It's very simple like that. And initially they only made a couple of those with the wiring specified by the spec of the machine. So that doesn't sound very useful, right? Because that's still a substitution cipher. But there's a reason why you make it a router. Because if you make it a rudder, there's two things that you can do. First, every time you press a key, one of the rudders at least will turn, which means you're starting to use a different cipher. The mapping from A to whatever letter changes every time you type a key, which means you basically become immune to the classic like frequency analysis and other basic anti-cryptography tools. And then if you change rudders, and you make sure that one of them can make the next one turn every, I don't know, like 26 keystrokes, for example, then you can build on complexity on complexity on complexity. And if your design is actually properly independent, you can make the combination explode, and it becomes impossible to just brute force it. There's no printer, because as we mentioned, this is a very simple mechanical device. Instead, there is what we call a reflector at the end. Which is like half a rudder. It's a full rudder, but the pins, the 26 pins are actually mapped one and one together. So what happens is your signal travels from the right side of the machine through every rotors, through the scrambling of the rotors, and then when it hits the reflector, it just gets back through another pin. It goes through the same machine again, and then it lights up one of 26 lights in front of the operator. So you type a key, the first rotor turns, then the signal gets through, and then through the power of electricity, simple basic electricity, one of the 26 lamps lights up, and that tells you what is the output. And every time you type, the rotor turns, and so you get a different encoding for every letter. And that's basically it. And it's kind of impressive, right? You get originally 3 rotors in any order, so you have 3 different rotors, mechanical rotors made by the company that made Enigma originally. So you can put them in any order to try to get 6 different combinations. Then, of course, you set them up in a specific position when you start the process. So that gives us like 26 times 26 times 26 possible keys. So that's 100,000 possible combination when you encipher a given message. That's not bad for 1920s, especially early 1920s, but, you know, that still doesn't look like a big number to me. Luckily, we can do better. The first thing you do is that they made the turnaround configurable, which is every 26 keystrokes, the rightmost rotor will make the one to the left turn 1, etc., etc., and you can configure the modulo on when it will do. So it's not every 26. It is every 26, but it might not start at the first keystroke or the 26th keystroke, which basically adds an extra pattern of obfuscation. And then the military variant said, no, that's not enough. We also need to have a plug board. And the plug board is just add another substitution cipher on the input and the output, which is just done by this, as you can see here. It's just a board. And the only thing you do is you pin things together to make combinations. You can technically make up to 13 pairs with 26 letters. The Germans use 6 and then 10. And then, as the war progressed, they were like worried that maybe this could be broken eventually. So they added more rotors. And in perfect retro engineering, like, oh, well, we would not prepare to do this. They added more rotors by slimming down the leftmost reflector and then adding a different rotor that was not exactly the same size, but it fit in the same box, and they did not have to make a new one. So you could use your past rotors and you could reuse your box. You just had to change some mechanics. Amazing the display of like old-timey, don't worry, we'll fix it later, and we'll retrofit some extra feature on top. And that's the one that was used by the Kriegsmarine, the Navy, and mostly importantly between the submarines. So with all those specs, what we get is you have to pick 4 rotors out of 10, because again the one on the left side is smaller than the other, so it's not interchangeable. So that one kind of breaks the combinations. Then you have obviously the 26 possible positions for each rotors, because that's the message key. Then you can decide when they turn and which offset internally they have. So that's another 3 times 26, because the left one, the leftmost one will not make anyone else turn, so it doesn't matter where it's set. And finally, you can make 10 arbitrary pairs, which is, I'm not going to try to recite that number, but it's big, right? I asked the internet, this is before AI, by the way, so I just actually use Wolfram Alpha. It's about, it's in the power of 26 combinations. Roughly speaking, if you do a log, it's about 62 bits, give or take. And again, 62 bits encryption, with a portable battery, a bunch of rotors, wheels, some wires, 26 lamp and a keyboard. I gotta say that's pretty impressive given the tech. There's no computer in there. How does that work? So you install the rotors. Originally, they install them every month, then every week, then every day. They change the combination of which rotor is supposed to be put in the machine, just for like operation safety. You set the rings, then you set the plug board to whatever pre-agreed combination, and then finally you put the key you want. And that's a very important thing that they realize very quickly. You don't actually type the whole message with it, because then you have a lot of corpuses of text every day that are exchanged using the same key. No, you pick a new key, you just encipher that key with the daily key, and then you go on. If you've ever looked at any modern implementation of cryptography, that's all they do, right? Like if you do like an RSA connection or whatever, they don't actually encode everything with your key all the day. They just immediately use that to exchange one key, and then they move on with that specific key, which immensely reduces the amount of text you can try to use to crack the key. And yeah, and then you type your message, and then obviously you have to prepend the message with the keys that you used for the day, so that people can decrypt it. So how did they break that? Because how do you break 72 bits encryption with like not even a computer? We go back to the Cipher Bureau because they are the first one who actually made the research. Because, as I think a lot of you knows, they were not really keen to the intention of the Germans back in the 30s, and they were like kind of really interested in what they would be saying behind closed doors. So this is Marian Rejewski. He was a mathematician and was one of the first ones who was hired to the Polish Cipher Bureau, which was their intelligence, crypto intelligence section. He managed to reverse engineer how the rotors were wired because the French managed to get a technical documentation. They posed as industrialists who were interested in buying the machine. They got the technical documentation and they used that to figure out how does it work. Turns out there's a lot of things you can do by just pretending to be an interested customer. So based on sales documentation and some very good intuition and math, he managed to figure out how the rotors 1 to 5 were encoded, because there was a few examples of decryption in the sales pitch. And just based on that, he was like, okay, so given how that works, given the input and the output and the keys given, this has to be this combination of wiring of rotors. And he made the Bomba, which is the original machine designed to crack Enigma, and all of this was shared later on as it looked like the war was going to be imminent. The Bomba is extremely interesting because it's based on one simple principle, which is that the Germans noticed at first that they were worried that if you typed the key early on with only like, remember the original machine had only 3 rotors. If you only have the first 3 characters in the message that are the key, and telegraph and radio telegraph are not super are prone to human errors. Like you might confuse a short beat with a long beep when the transcription happens or something like that. They were worried that if someone did not get the key correctly, then the whole message would be garbled. So they repeated it twice to increase the chances that the person on the receiving end would be able to get it. But that gave the poles a property that they could try to work with. It doesn't matter what the message say. You already know that characters 1 and 0 and 3, 1 and 4, and 2 and 5 are the same ones. So they built 6 machines because there was technically only 6 possible configuration that you could do with the 3 rotors. So they built 6 machines that just all encoded the substitution tables of the Enigma machine, and they just say try all the combination one by one, and basically stop the mechanism when those 2 pins output the same signals, and then those 2 pins and those 2 pins. Like if those 3 output the same signals, then you crack the key. Because obviously it's very likely that it cracks the key because like collisions are very unlikely to happen. And that was good enough. And they basically could read most of it until the war started. The Germans finally noticed that this was dangerous as a practice, so they stopped repeating the keys later. And that's why when Turing team took over, they changed something and they start looking for what they call cribs, which is repeated expressions of formality. Basically, trying to guess what the plain text was to try to see if they could find a collision with the actual key. For example, one of the staff aides of General Rommel was an extremely polite man. And he started every communication with HQ with the same very verbose, polite opening phrase, like, oh, to my dear, blah, 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 something like that. So they knew that when it came from Rommel HQ, the start of the message was almost guaranteed to be the same 15 characters every time. And again, remember, the key is the same every day. So as long as one message reuses too much data that you can predict, then you can run a machine that will basically try to detect a collision and say, hey, this is probably the key they used. And then you can decrypt the whole thing the whole day. And it worked. Like, the Allies were able to read everything the Germans said most days during the entire war. And the Germans started wondering, especially when they kept getting their subs caught in the Atlantic, that maybe somebody was able to read something. They ordered internal audits, and they conclude that theoretically that's possible, but practically there's no way they did it. And even like Americans actually interrogated like prisoners of war in the German intelligence after the war. They were absolutely convinced that Enigma had not been broken until the end of the war. That's a lot of history. Now let's do some C++. So as I said, sometimes you can work smarter and not harder. I'm going to do the opposite because my computer can do things that Turing cannot even dream in his mind. So again, we go back to 62 bits, right? That's the numbers. How hard can it be to break it? We need a data set first. I picked this one because it's actually interesting because it was not decrypted during the war. It's a telegram that was found in a sync sub outside of the coast of Norway. In the 80s, right in the 90s, and contained about 50 messages. I did not crack them myself. Somebody set up a project in the 2010s called Enigma at Home. Has anyone ever heard of like SETI at home and things like that? Okay, some of you. For people who are not my generation of before, this was kind of like when you could mine crypto at home, but it was actually useful. You could like help science or something like that. He basically gave the same idea. Here is a small client you can run at home. It will connect to a server, give you like a small bit of the key space that you can try to brute force on your own machine. And then eventually, with basically distributed computing, they managed to break a lot of things. So okay, that gives us a baseline. In 2012, you needed to do like a collective computer thing to be able to break that message. Can I do it with a single machine? It's been like, it was 10 years when I did it. It's 13 years now. And you know, the computers have changed a lot since. So I'm going to pick one message for several reasons. One of them is because it's longer than the recommended length by the German services. That gives us more characters to try to go through. But more importantly, because it's actually a very important message. This is the encrypted message, which obviously is unreadable because it's encoded with Enigma. This is the decoded message, which, to be fair, looks just about as garbled, but technically this is German. That's probably why you think this is still garbled. But if we start looking at some words, now we start saying, wait a minute, I don't think those words are random. They sound a lot like the bunch of things that Germans would be saying in 1945. It's using a lot of abbreviation for German military slang, so I'm not even an expert myself, but luckily some smart people do. What it is saying is that Grand Admiral Donitz is now in effective command of whole of Germany. What he's saying to everybody and to the world is that Germany is running out of Nazis to run the fucking country. And effectively, a couple days after this telegram was sent, Donetsk, right here, surrounded by the Allies, will surrender and end World War II for the European theater. So now that we have a whole bunch of stuff, let's try to crack it. So, 62 bits brute force. That's actually the equivalent of trying to break SHA-1 or SHA-1 with the collisions that that people have found. So that's the equivalent of knowing where the failures of SHA-1 are today, and the reason why we don't use it anymore. This has much complexity to break it. Like, I'm sure the NSA can do it, but I'm not sure I can. So let's see. I'm gonna try by dividing the problem into two. Maybe if I can figure out the rotors and all the internals of the machine first, and then I can attack the plug board in a second space. In a second bit, I can divide the problem in two. That's usually what happens when you try looking for collision, right? We try to say, okay, do 62 bits are actually not 62 bits because there is a relationship between those two. So what if I try to split the problem and, you know, leave the plug board to as an exercise to the reader? So we still have 35 trillion combinations. We can also probably ignore the fact that the leftmost rotor will turn eventually, because again, like it takes 26 for the first rotor to turn, then 26 and 26 for the second one, then 26 and blah blah blah. So as you might guess, unless you're typing a novel, the leftmost rotor will never turn. It will always use the same one. So there is already some things we can ignore there. So that allows us to divide the space again by 26, which is 208 billions. I'm not like big on numbers, but that sounds like a number that is roughly possible to attack. Like, you know, my computer is 4 gigahertz, right? So that's 4 billion instructions per second. I have 16 cores. It's obviously more than 1 instructions to be able to attack this, but that sounds like roughly the same ballpark. So, okay, let's try something simple, right? For every permutation of the rotors, for every permutation of the ring settings of the rightmost two rightmost rotors, for every possible key, just try to see if we match the plain text, because we know what the message is, which is kind of emulating what people did at the time. I know what the message is. I just want to crack the key, because once I do that, then I can apply that key to decrypt everything else. Especially because announcements are usually sent both encrypted and in plain text on other channels, because it's a big announcement. So that was also a way that people attacked things at the time. They would send announcement encrypted to submarines, but then they would send it in plain text over the radio because they had to communicate it, and they were like, who cares? Like, everybody's going to know anyway. But they use the same key, so that's good enough for us. So let's try to do that. So here is the code, finally. So what do we do? First, we have to go through the plug board. Assume that we know the plug board for now, right? So we have the setup of the plug board. What is the plug board? It's just a table of 26 characters, and for every offset, it basically gives you the offset of the next like letter that it maps to. So like if you have A and E that are staggered plugged together, then your input is 0 and your output is 4, right? Because E is the fourth letter of the alphabet. Then you go to the rightmost rotor. Then you go to the middle right rotor, then the middle left rotor, and then the middle the rightmost rotors. And every time you have to take into account the ring offsets and the offsets of which one it is, because you're basically what you're doing is you're simulating where the current is passing. Because there is only at any point 2 pins that are actually connected. All the other ones, they are connected, but there's no power between them. So that's what we're simulating. And then since there is a reflector, what we do is that we simulate the reflector going back. The position of the reflector is fixed. It was cracked like very early on when somebody figured out a copy of the reflector. We know how it works. There's nothing to crack in there. And then we just do the same thing on the way back, right? So we go back to the leftmost rotor because we're going back on the other direction, and we simulate the current going all the way to the actual light system. And there is a magic wheel called ETW, entry wheel, I think, or something like it's called. It's a technical thing. It's the way it was. It's the way the wires were wired to connect to the lamps for the output system. But again, it's a fixed wheel. We know how it is. It's a 1-to-1 table that is already known. So how do we do a rotor? As I mentioned, basically, it's 26 characters, and all we need to do is have the wiring array forward and backwards, because we don't want to be doing like a linear search to try to go backwards through the rotor. So what we do is we just generate the opposite function, the inverse function of that array on a second table. And we generate it 3 times. I will explain why we do it 3 times. And for fun, since this is C++, and I was doing this in 2022, I tried to do it at compile time, because at the time, Kunstexpert was pretty cool. It's still cool, but it was more new when I did it. And importantly, we're trying to avoid a modulo, and I will explain why. Because here's the thing, right? This is your rotor. I think this is the first of the 7 possible rotors. This is the wiring, right? Like A maps to E, B maps to K, C maps to M, blah, 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 blah. Okay, so when we want to simulate it, that's how the rotor turns, right? Every time it turns, the mapping changes because the rotor is turning. That's what we want to simulate. And when we try to do this, basically what we do is we take the input, we add the offset depending on which ring setting you have, and where and how many times we have turned so far, and that tells us where we go, right? Like if we're in position 0, it means that we have to, or like if we're in position 0, it means we haven't turned at all. Then we have 1 if we have type 1 character, etc. Just simulate the fact that the rotor is turning. What is his current position compared to the default one? The problem when you do this is that there's a problem. You might go before or after your array, because if you have almost turned entirely and someone type like a Z, you will head up outside of bound, right? Because technically, if you look at the math here, obviously it doesn't work because input plus offset can go over 26. And likewise, when we start implementing the ring settings, we can have a negative offset. We can also go before. We can also have a negative offset. You can fix that by doing a modulo. That's the very easy way of implementing this operation. This is not a good way of implementing this operation because this is what it looks like. I told you there was some code. This is a modulo 26 on a modern computer. That sounds like a lot of code for just doing a modulo 26. Luckily, people have found a solution. I did not come up with it, by the way. Like this was found by Enigma aficionados back over 10 years ago. But if you repeat the same table 3 times, and you add 26 to the base offset, then every time you land out of bound, you actually don't land out of bound. You land exactly where you should be landing, because what the modulo is doing is pretending that this thing loops forever. We don't need to loop forever. We only need to loop 1 time backward and 1 time upward, and that's the maximum bounds we can ever get. We can prove this. And that way, the operation just becomes an index with a sum, which is that code to the right. And just if you don't see exactly, this is basically the same code minus the modulo. And I also checked if we needed to have the plus 26. I tried a bunch of things with like manual offsets. Manual offsets do not change the computation cycles. So like for example, one of my implementation, at first I used the actual ASCII code of every letter, and then I say, oh, what if I made it 0 indexed instead, so that I don't have to do minus A or something like that. It is transparent for your computer. Like adding an int or adding an int plus a constant is exactly the same amount of cycles on a modern computer. It doesn't matter. So I kept the internal representation in ASCII because that way it was easier to debug. I didn't have to remember which letter is number 6. I could just look at the code. So with all those permutations, we say, okay, worst case scenario, 200 billion and we're done, right? This is an ETA estimation. It's about as reliable as an actual file copy estimation on Windows, but that gives you an idea, right? Okay. In the realm of possibility, because 3,000 minutes is just leave the computer on for a while, but that's still like, I'm too impatient for this. So 52 hours, something like that. Maybe we could do better. So, hey, I mentioned the fact that I have 16 threads, right? Why would I use only one? This is a very simply and easily multi-threadable process. My math says that I can just divide the time by 16 just by using more cores. And also, I have C++17, so it's kind of easy, actually. I just, for simplicity, I just made an array that I use an iota to fill from 0 to 25. And then I just use a for each that just at some point in my nested loops, I just replaced one of my fors by a for each from 0 to 26 with the same for each, but I just add execution parent sec. Surprisingly, that was good enough. I did this on Windows, by the way, but as far as I know, it's the same everywhere. Because most implementation of 17 execution, they are smart enough to have a basic job system behind it that spawns 1 thread per core you have available on the machine, so you don't get any problem with oversubscription, blah blah blah. I checked. I put some profiling data. It just spins 16 cores because I have 16 cores on my machine, and each one of them gets a chunk of that iteration, and that's done. That was pretty good, but I also gonna go and say I still want it to be faster than 10 hours or 5 hours. So what if we cut the complexity? Because here's the thing, right? The leftmost, the middle left rotors is unlikely to turn much, because again, 26 times 26, it would take 1676 keystrokes for it to turn once. So at most one time in the message, its wiring will change. Everywhere else, it's a constant. So it's probably a waste to iterate through all the settings, because like even if it happens in the middle of the message, I can still read the other half clear as day, and it's still impossible that it will be like a coincidence. So that's what I did. I just assumed that the rotor was 0, and just say, hey, if we can match like at least a quarter of the decrypt, I think math can prove that you should at least always get half, unless the message is long enough. Then you're still good. You just have to fine tune like one of the 26 settings. We split the problem. We put that 26 loop outside of the normal thing, and then we do 26 passes at the end just to fine tune and get the whole message. And that was pretty good, because that broke the search space to 8 billions. And 8 billions is something you can do in 6 minutes. My machine, like 10th generation, not this laptop, but the one I have at home, could do this in about 6-7 minutes. This ETA, again, is not perfect. And also it stops the minute it gets the key, which is somewhere in the middle of the space. But in a matter of 5 minutes, you basically crack it. That's not too bad. But now we say, okay, but you're not cracking the plug board, Mathieu, right? You remember those times 200 trillions that you kind of ignored practically? Like, they're still there. So is there a way we can actually split the problem? Because, you know, that's a problem. We can't brute force that. Like, it's already hard enough for this. Okay, I'm going to have to go much faster. So can we split the problem? And the answer is yes. Because again, remember, out of 26 characters, only 20 of them are actually plugged, because we put 10 pairs. So 6 of them will actually be correct. 6 of them will be good and will actually give the good output. So what we do is, what if we brute force with an empty plug board, assume that nothing is plugged, and then get how many characters are matched in the right position. And with some heuristic, you say, okay, you know, this message is mostly garbled, but the E's and the F's and the G's are always in the right position. That sounds too unlikely to be abnormal. And that's the one I did for this actual message. The green ones are the ones that actually end up in the right position, even if you don't have the right plug board. And the purple ones are the ones who are wrong, but still have a high count. And you will notice that the G's, the I's, and the O's and the T's are in the position correctly in the whole message. And basically, I made some basic math and say, you know what? If the score you get is about 1/10 of the message, it's unlikely to be a coincidence. So assume you get the score. And then there are algorithms online to crack the plug board itself that I don't really want to get up because I'm short on time right now. Then I try to see, can I do it even better? And I say, what if I ignore the ring settings entirely? Like, the turnover will be wrong, but on a period of 26 or something characters, the message will be correct, right? Because as the person types, if the ring settings are wrong, it will turn too early or too late. So for a repeating cycle of about 26 characters, things will be roughly wrong, and then they will reset themselves every time we hit the offset, and it will continue. It's not 26; it's like wherever your difference between the actual position you guessed and the real one is. But what I mean is, like, yeah, if the setting is wrong, I will have 25 good characters, 1 wrong characters, etc., etc. If the ring setting is 13, I will have 13 correct characters, 13 garbage, and then 13 good characters again. And then you can just do a fine-tuning of just try only the to tweak the rings once you have the thing and see if you improve the quality of the decrypt. And yeah, I got something that runs in basically a minute and gives us the actual correct setting at the end. This is actually what was used for this message. That might not work with all messages. Again, this is a fun project I did one summer. I know that there's some research that have been published. I reread for this talk. I reread a paper from 2017 that explains a bit what people have tried. You can improve it. One of the things you can do is find the most common letter in the original message in the decrypt, and try to plug it with all 26 possibilities, and see if you get a better match. And that's usually good enough to get you to about 15% of the message correct, rough. That's enough to distinguish it from noise, which is the whole point of Enigma, right? And the whole idea of this whole decryption is that if you can get enough things that that you can distinguish from noise, you're probably correct. Because at the end of the day, you're kind of playing the game like Mastermind, or maybe on a more modern thing like Wordle or something else. You know, like the thing tells you, hey, you're not really decrypting this correctly, but it kind of gives you a hint that you're on the right track, which is how it was broken historically, right? Every time your crypto is not actually like the whole idea of modern cryptography is if you change one bit, you should flip at least 50 half the bits in the output. This one clearly doesn't do that. If you get some of it wrong, you get some of the message correct, and that's good enough for you to try fine-tuning and trying to find the solutions. I have thought about doing a compute shader or some form of GPU assist, because that sounds like the kind of thing that the GPU would be even better at cracking than a CPU, because it's a very dumb problem that you have to attack with a huge space of parameters. Again, I had 45 minutes, so I'll leave that as an exercise if any of you like to write compute shaders. And purists will argue that this is not ciphertext only, right? I already knew the message outside, and I didn't try to crack it only knowing some jargon like Turing did. I have some explanation of how to do it in the longer version of this talk, but I have to keep it short here. What V++ did I use in there? Again, it was done a couple years ago, but still, Kunstexper algorithm and basically all the relaxation around Kunstexper allowed me to generate the wheels with the 3 times repetition at compile time. I had a lot of string views and spans. I lost string views and I lost spans. I didn't have any copies of anything anywhere when I was scanning the messages and things like that. Of course, C++17 parallel algorithm to turn my thing into a 16 core, 16 threads like a brute force attempt. Took me like literally 3 lines and a pound include at the top for execution. I didn't have to add any third party setup TBB and whatnot. It was just basically working out of the box. Back at the time, I could use C++ 20 formats. Sadly, I was not allowed to use println because it only came in C++ 23. I considered using range to iterate word combinations because you have to generate all the possible combination of all the rotors. I just felt a bunch of for loops were simple enough. Don't attack me. Coroutines to try to simulate the thing running again seemed like overkill, so I just stepped there. The new version that I have updated on my machine has println now instead of format plus cout, but at the time would have been great to have it. At least everybody has it now. So, in conclusion, Enigma is not a recommended cipher in 2025. Just don't go home and try to use it. I guess I was proven incorrect. You can't just attack a 60-bit cipher just because you have a huge computer. You're still going to have to be smart about it. And maybe that's a lesson about how about optimization in general. Yes, my computer is big. Yes, it can do a lot of things. Yes, it can do 4 billion times 16 instructions per second. Yeah, it's still not going to be able to do something unless I'm smart about it. And that works for both like the micro-optimization of the modulo, but also for things like, what if I split the problem into 2 different bits that I can just have to add instead of multiply together in terms of complexity? And finally, even if you go on a tangent and rabbit hole on a weird summer, you will still end up figuring out that, oh yeah, some of those new features, even on a toy project, they're kind of useful. They changed the way I wrote code. I could use a bunch of stuff. It was not just that I forced myself. If I had forced myself, I would have used coroutines and etc. But yeah, there was still a bunch of stuff there. So that was great. Thank you.
Unbelievable, just unbelievable. And thank you for deciphering history as well. Thank you so much.
We should take question because this is a fake out. There's one question that remains, and unless you guessed it, maybe I will ask the question for you, and then you can ask me a real question. Because there's something missing from the whole story, if you remind me what I said at the beginning. What happened to Rejewski and the Polish Cipher Bureau? Because at the end of my introduction, I said that they managed to make it safely to France. So, you know, they joined PC Bruno, the cryptography team in Paris in '39. And the Allies spent a lot of effort to crack Enigma. They had the man that had cracked it originally at hand. So why haven't we heard of him? Why are we only talking about Turing? What's going on here? So, well, what got on is that France got a problem in the summer of 1940, called the Ardennes, and a few other issues. And so the PC Bruno, the cryptology team from France, had to be evacuated. But surprisingly, they didn't flee to England. They flew to North Africa, and then they came back. And they hid in southern France for 2 years in this house. You can actually rent it on Airbnb. That's where I found the photos. That's absolutely insane. In southern France, they were working on cracking Italian and Spanish code because they had a copy of Enigma that was given to them by the Germans. And they stayed there until Germany invaded France a second time in 1942 and trying to take over Vichy. They tried to cross the Pyrenees in the middle of winter. They were betrayed by their guide, who robbed them at gunpoint and left them alone in the darkness. They still managed to make it to Spain in the middle of the night. They got caught by the Spaniards. They ended up in a jail with staffed by Franco. But the Polish Red Cross managed to negotiate their release, and they finally made it to the UK in late '43. But by then, Bletchley Park was top secret. And the Brits did not trust the man who had been so long in like France, Vichy France, a bunch of other places. It was on a need-to-know basis, and he could not be allowed to talk about it. And most of it was made public in '73, '74, when those two intelligence officers, French and British, published a book about what actually happened. But what if? What if they had collaborated? What if the first computer was not designed just by Turing, but by both of them? Could we have cons by default? Could we have no such thing as ill form, no diagnostic required? Could we have modules that actually work on every compiler and every IDE without a hack? I don't know. I just like dreaming. And furthermore, I still think your build should be destroyed. Thank you.
Not only a specialist on the topic of Polish-based, let's say, Enigma, but also a stand-up person and comedian. Thank you so much.
Thank
Hit
you.
the 5 right here. Thank you. And if you have any questions whatsoever, I think we still have a microphone, so feel free. I mean, it's just like for the joy of that, for probably. In just a couple of minutes, please do not go so fast, because we have still Eva Kołotowicz, who is going to join us in a couple of more minutes right here on this stage. There is a nice surprise from her, I think, and if you stay with us and you stay tuned for a couple of more minutes, I think you should be happy. If not, and there are no questions and no one is willing to speak up, so I think once
Scary.
you are just Enigma to us, okay? So please just give a warm applause once again. Thank you so much.
Thank you so much.
Thank you. Mathieu Ropert was the hero